All right, so we're basically done, well, sort of. We're basically done, let's say we're done with definite integrals, going back to an application of indefinite integrals, right? So we're basically on to our last topic. Now, if you're studying engineering or science, or maths, of course, in my opinion, differential equations is one of the most important topics that you learn about, because differential equations basically model the real world. So if you're doing engineering or physics or something, if you've ever got to use an equation to calculate something, you know, like the current in a circuit for a particular time t. So I'm a chemical engineer, so I have formulas like how long it takes to empty a tank, you know, stuff like that. Almost every single one of those formulas comes from solving a differential equation. We don't tell you that in first year because you haven't done them yet, right? And differential equations is a very rich and active area of mathematics. So most applied mathematicians like me, I actually spend most of my life solving differential equations. I find them absolutely fascinating, that model the real world. And you're already actually used to doing this. We're just not telling you that's what we're doing, right? So a perfect example is when we do integration by parts, for example. Let's say I asked you to integrate that, right? You would say, well, you let u equal x, and off you go. Now this bit here, what you're actually solving is you're looking for a function, v, whose derivative you know, but you don't know the function, right? That is a differential equation, right? Another one is when you do physics. If you know, everyone knows that, anyone does physics anyway, forces mass times acceleration. And of course acceleration is the first derivative of velocity, or the second derivative of position with respect to time. Right? And so if you want the velocity or the position, right, you integrate both sides, right? And you can find them. That's a differential equation, right? Now these are very, very simple differential equations, but they are differential equations nonetheless. The complexity of differential equation gets very hard very quickly, and there's lots of differential equations that we can't solve. All right, but essentially, hurry up. Right, we have, you know, as I say here, a vast number of situations, especially if you're modelling a system, this is actually discussed in the unit reader. None of it's examinable, but there's a couple of examples in the beginning of the differential equations chapter in the unit reader about, you know, there's, I think, the example about emptying a tank and population growth and all that. You've probably done this before. And all of them come from solving differential equations. So in general, what you're looking for, you're looking for a particular function. Actually, you're looking for every possible function and all you know about it is what its derivative is doing. You don't know what the actual function, that's what you're looking for. That's what we call the solution of the differential equation. Now, the simplest case is a single function of a single independent variable, right? So the derivatives are ordinary derivatives, and we call those ordinary differential equations, or ODE for short. A situation where we have a function with lots of independent variables, then we have partial derivatives involved. Those are called partial differential equations. We won't look at those ones in this unit. Being able to solve partial differential equations requires a lot of groundwork, which you haven't done yet. It needs a concept of Fourier series and some concepts from linear algebra that some of you may have already done in 1012, but most of you will do next semester. So those of you who are studying maths, you'll see partial differential equations in second year when you do Introduction to Applied Maths. Those of you who are doing engineering, you'll see it, touch on it in some of your engineering and do a third year math unit where you'll learn about it, called Advanced Engineering Mathematics. And in physics, you will learn about it in physics, right? And with some math, with the second year unit, what's it called? Math Methods 3 or something, I can't remember what the hell it's called. But you'll see it, right? We're not going to see partial differential equations here. Notationally, it's easy to tell the difference. If it's got ordinary derivatives only, it's an ordinary differential equation. If it's got partial derivatives in it, it's a partial differential equation. All right, so the first one, this one, if you wanted to solve this first one here, what you are looking for is a function f of x and y that if you find that, and all you know is that if you find partial df dx and add it to partial df dy, it equals f squared. That's all, and you've got to try and find a function f that works. Solving that is a lot of work, right? That's called a quasi-linear first-order partial differential equation, and you use a technique called method of characteristics, something you'll learn about much later on. Far too difficult at this stage for you. Second one is we're looking for a function f that's only a function of x because it's only got ordinary derivatives, where that if you know that the second derivative plus 3 times the first derivative plus 2 times the function equals x to the 4, find f. Right? And that's called a second order linear constant coefficient non-homogeneous differential equation. Right? Bit of a mouthful. We will do ones next week where the right hand side is 0. We'll learn how to solve those ones. Right? Now, the order of a differential equation is the degree of the highest derivative that occurs in it. Right? So the first one is a first order partial differential equation. And the second one is a second order ordinary differential equation. Right? An important class of differential equations are ones that are linear, and by linear we mean linear in the function we're looking for, not linear in the other variables. The x's we don't care about. So this one is non-linear because it's got an f squared. Right? It's non-linear in f. This one is linear because it's linear in f and its derivatives. This bit doesn't matter. Right? Yes, that's non-linear in x, but it's linear in the function we're looking for. Right? And we're only going to do second order linear, and first order we'll do linear and ones that are called separable, and that's all we'll have time for. Now, essentially what we want to do is we want to solve them. Right? Let's go back to what we know. If I asked you to solve a quadratic equation, then you're looking for particular values of x that are constants, if they exist, and we're only interested in real things here. We're looking for two numbers that work. Where you plug them in the left, you get 0. We all know how to do that. A differential equation, on the other hand, is we're looking for functions that work. Plug them in the left, it equals the right. And not only are we looking for functions, we're looking for all of them, all possible functions. Right, here's a simple example. Let's say this is called a first order linear, and it's a first order separable differential equation in y. I'm looking for a function y such that when its derivative equals 3 times itself. Right? And it turns out that we'll find next week that we can solve this. The solution is, one solution is e to the 3x. Shouldn't come as too much of a surprise that the exponential function appears. The exponential function is the only function whose derivative equals itself. Right? So a lot of the time, exponentials, when they're linear, exponentials pop out. Right? And of course, with the 3 out the front, you can e to the 3x, the derivative of e to the 3x is of course 3e to the 3x. That's the left-hand side. The right-hand side is 3e to the 3. Done. But it turns out that any constant multiple of e to the 3x also works. The derivative of c e to the 3 is 3c e to the 3x, no matter what c is, except 0, of course, because that's a stupid solution, right? Right? And you plug it in the right, you get the same thing. Right? So this we call the general solution, and that is what we're looking for. We want one particular one if we have what's called an initial value problem, or as you go higher order, boundary value problem. We'll talk a bit more about that later. Where does this constant come from? Well, if you want to solve this differential equation, formally, you need to undo the derivative to find it, don't you? Right? So it will involve integration somehow, indefinite integration. Right? That c is the plus c. Right? And this is why we are so pedantic with the plus c in indefinite integrals. It's not us being stupidly mean. There is a reason. And the reason primarily is when we solve differential equations, that plus c can be crucial, right? Because we're looking for all possible solutions. Right, to verify solutions, basically it's like if you solve a quadratic and you want to verify your answer, so if we solve this quadratic, we find x equals 1 or 2. If you want to check your answer, what do? Well, you plug x equals 1 and make sure you get 0, don't you? So you get 1 minus 3 plus 2, that's 0. X equals 2, you get 4 minus 6, that's 0. Verified. Right? I'm happy. Same thing with differential equations. If we want to verify a solution, we plug it in the left and make sure it equals the right. So for example, let's have a look at this differential equation. This is a second order linear differential equation. It's technically it's called a second order linear constant coefficient non-homogeneous differential equation. Right? Not one we're going to solve in this unit, but it turns out that's the solution. The first thing, look how terrible it looks. Right? There is a systematic way to find it, believe it or not. Right? This one you use a technique called method of undetermined coefficients or method of variation of parameters, something you'll learn about in a different unit. But if I want to, is that a solution? I plug it in the left and make sure it equals the right. So I need its second derivative. So if I just calculate the derivative twice, I get that 4, and here we've got to, the constants are serving a purpose, so we can't change them once we've started. Right, so the second derivative it turns out is 4c1, all that, right, I'm not saying all that out in words. Plug that in the left, second derivative minus 4 times the function equals the right, it is a solution. Right, and notice again that the constants don't matter. Right, it works no matter what the value of the constants. Right, so technically there's an infinite family of solutions to this differential equation. Right? And that's what we mean by verify. We can do the same with partial derivatives. It turns out this is a first order quasi-linear partial differential equation. Right? And there's a very neat way to solve them, but it involves things you haven't heard of yet. Right? But it is a very neat way to do it. And it turns out there are two solutions. The first thing to note is those two solutions are totally different. Right? And this is one of the other problems with partial differential equations. Uniqueness is not guaranteed. With ordinary differential equations, provided some conditions are met, uniqueness is up to constants. Uniqueness is guaranteed. And that's something, again, you'll learn about later on. For this unit, every DE I give you will have a unique solution, minus constants, of course. Right? But to check both work, I need partial df dx, partial df dy. I do it on the first one, plug it in the left, it equals the right. I can do the same with the second one. Right? So they're both solutions. But the interesting thing here is that those two are totally different things, totally different looking, but they both work. Right? And there is a way we could find both. Right? So partial differential equations is fascinating. It takes up almost a whole unit on its own, having to solve partial differential equations. Now, we're going to look at only some specific cases. It turns out that what we learned for second order differential equations works for third, fourth, fifth, and so on. It's a logical extension, although the algebra gets hairy, it keeps working. But there is only a small handful of second order differential equations we can systematically solve. That's what makes differential equations so difficult. And it stems from the fact that, as we see, definite integration can't always be done, which means there are differential equations we can't solve, right? That we have to come up with clever ways to do it. And we can do things like use Taylor polynomials, that sort of thing, if we need to, or use a computer. Right? And so we're going to look at first order separable, first order linear, and second order linear constant coefficient homogeneous. Right? I know it's a mouthful. They're the only ones we're going to look at. So the partial differential equations, don't have time to do it. Certainly not a week's not nearly long enough. With first order differential equations are unique. One, there is a lot we can do, and there's a lot of general solution strategies. In fact, there are several types of first order differential equations that we can solve, provided we can do the indefinite integral step that will be hidden in there somewhere. There's separable, linear, exact, homogeneous Bernoulli differential equations, first order, and we can solve them all. Then there's a couple that have a name that we can't always solve, Abel, Riccati and Chinny first order DEs, that sometimes we can, sometimes we can't. When we get to second order, all bets are off. If it's constant coefficient, life is good. If it's not, crap. Right? And it comes up and you need a lot of skill to do, and that's what applied mathematicians do. We use our knowledge to try and solve differential equations. Let me show. I've always found differential equations quite fascinating. Let me show you a simple example. Let's imagine this one. Everyone see? Yeah. I'm looking for a function, dy dx, whose derivative equals e to the y. Now, if that was e to the x, y is e to the x, isn't it? Done. Right? But e to the y, well, that's a bit more complicated. Right? This is an example of a first order separable differential. We're going to see how we solve those next week. It turns out the solution is that, where c is an arbitrary constant, any constant. Right? First thing you notice, well, maybe it's not so surprising there's a log in there, but with the exponentials and logs, but it's not obvious by inspection, is it? If it was dy dx equals e to the x, like you could almost do it without thinking. But when the dependent variable's there as well, no idea what will happen. Right? And we can see this is the case because if I differentiate this, I've left all the steps out. You use the chain rule and so on and so forth. But the derivative of that is that, which you'll notice is, if I take the exponential of this, right, is the same thing. It's e to the y. Right? So it is a solution. First orders, a lot of them we can do, even if they are terribly complicated. Linear or non-linear. But second order and higher non-linear, so this is non-linear because it's non-linear in the function we're looking for. Why? Because of the presence of e to the y. Solving this one would take me about 2 solid pages of algebra, believe it or not. Right? This is not one we're going to be doing. Right? The way we solve it is very weird. But it turns out the solution of this one is, which I am not going to confirm, trust me, what the hell? Right? That is the solution. Here C1 and C2 are arbitrary constants. Notice that the first order has one constant, right? Because informally, you've got to undo the first derivative, you bring one constant in. The second one involves 2 constant because formally, to undo the second derivative, you've got to integrate it twice. 2 plus C's, right? Which we label C1 or C. You can call them whatever you want, A and B. Most people just call them C1 and C2. But the thing is, where the hell did that solution come from? You can verify it. You have to differentiate that twice. Have fun. Right? But you can. It is the correct solution. Right? But the thing is, the first one is a standard solution technique that we'll learn next week. The second one takes some ingenuity to solve it. Right? And let me give you a hint. How would you can't integrate the left with respect to, I can't integrate e to the y with respect to x. Right? So how would you even get started? The trick with this one, if I multiply both sides by dy dx, assuming dy dx is not 0, y is a constant, I don't want that solution, that's useless. Right? So I can safely assume that y is not a constant. Right? So if I do that, I can actually then integrate both sides with respect to x. Because what I'll get is right? Now, why does that work? If I differentiate the left with respect to x, chain rule, it's a half times 2 times dy dx times dy squared dx squared, isn't it? Yeah? And differentiate the right with the chain rule, y is a function of x, I get y dash e to the y. Right? And then I have to solve. Now that's a first order separable. A very bad one, but a first order separable. That will require a nasty inverse trig substitution to solve. And that's where the tan comes from. Right? So sometimes you have to be ingenious with second order and higher non-linear takes years of practice. What about a third order? Impossible. Can't be done. You cannot find a function whose third derivative equals e to the y. Yes?
With that, like what you did for the second derivative, couldn't you just, because effectively with that second differential equation, the first derivative for that equation would be what you got for y in the first order version?
No, you have to undo 2 derivatives to find y. Right? So I need to integrate it. I need to find. A lot of the time, what we do is try and turn them into first orders because we have a wide variety of techniques to handle first orders only.
But could you, so you've got with that first bit, you like
This bit.
the derivative
Sorry.
top of the page.
Top of the page.
So like for that one, you showed that the derivative of ln 1 over ck dx is e to the y.
Yep.
Couldn't you effectively do as that second?
You could try guessing. Yes, that's basically what you could try and guess it. Who would have guessed that?
I mean, more like you have like dy dx equals ln of 1 over ck dx.
Yeah.
And you find that, wouldn't you try to integrate that?
No, well, once you've got the solution, you've got it. Right? You've got to imagine what we're doing here is we don't have that in the first place. Right? All I'm doing is verifying it. Right? That the solution I've got's done. So the main thing is second and higher order, the difficulty rises exponentially. Right? So, and then this one is impossible. So non-linears are really hard. I mean, most applied mathematicians spend their life solving non-linear problems because they're the interesting ones. Right? Solving linear ones is boring to us. Right? But that's about all we can handle a lot of the time. Anyway. But before we get to actually solving them next week, with first orders in particular, there is some things we can do to get a feel for the solution. Right? So first orders are unique. There's a lot we can do. Second and higher order, there's not a lot we can do. But first orders there is. And usually I find that mastering skill in differential equations means you master the first order ones first. It's a bit like all the different integration strategies we've done. They're all very different, aren't they? But they all build your knowledge and skill to handle more complicated intervals, hopefully. All right? It's the same with differential equations. Concentrate on first order, learn everything you can about first order, then hopefully those skills will give you intuition to solve second and higher order non-linear ones. Right? And there's actually a lot of things we can do with first order ones. Now, first order differential equations, most of them, not all of them, so one that we can't are called Clarow and D'Alembert differential equations, first order, which are awful things. But most ones can be written as dy on dx equals some given function of x and y, and you're looking for y. Right? Now, if y is not here, so if the right hand side is just a function of x, you just integrate, you're done. As long as you can do the integral, it's done. Right? But when the y appears, the unknown function on the right, that's where things get hairy. Right? The other type is if this was to a power. Right? So if this was, say, all squared or square root or something like that, those ones can get a bit hairy as well. We're not going to do those ones. So all the first order differential equations we're going to look at can be written in this form. F is given, y is what you're looking for. right? And we'll do ones where the right-hand side is where these are separable or linear only. We're going to see those next week. But before we even start, what is this actually saying? Right? I'm looking for a function, y, and all I know is what its derivative is doing. That's all I know. Right? But surely I could glean something from that information. Right? And one thing we can do is create what's called a direction field. What is this saying? Remember, this function f is known. So what this is saying is you know the slope of the function you're looking for all values x and y. Wherever I am, I know its slope. I know where it's heading. Right? So if I plotted them all out, say I pick a suitable region of the xy plane and draw some little arrows to tell me where the slope's pointing, I could sort of trace out a curve that would be a valid solution. I've just got to find it. Right? But I can get a feel for what the solution looks like before I try and attack the differential equation. And this we call a direction field or a slope field, one or the other. Right? So this differential equation means that any point in the xy plane, obviously where this function f is well behaved, if you can't take square roots and negatives, that sort of thing, all that means is, well, that there's no solution in that region. That's all. Right? No real solution. There might be complex ones. Differential equations with complex variables, awfully nasty thing to work with. Right? But this means that formally we can evaluate the derivative or the gradient and represent this graphically by a bunch of little arrows, little vectors that have x component 1 and y component dy dx. Right? If you do this for a whole bunch of them, you get what's called a direction field or a slope field. Now obviously I ain't going to get you to draw these by hand, right? But here's one for the differential equation dy dx equals y squared minus x squared. Right? So between x is minus 2 and 2 and y is minus 2 and 2, basically at the beginning of all those little vectors I'm calculating its derivative. Right? So for example, at, I don't know, let's say it, where's a point where, let's say it, I don't know, what's that? That's x equals minus 1, y is a half, roughly. Right? Oh. So that's what's a quarter minus 1 minus 3/4. So obviously negative pointing down, right? And I can say, well, that's about right. So the steeper that way, it's bigger in the negative direction. And from this, you can say, well, I can see a whole family of solutions. So there's some solutions that follow these little arrows. If it's down here a bit, it looks like this. If it's down here, it looks like this. Remember, there's lots of solutions because there's an arbitrary constant floating around in here. Right? So they're just different constants. Right? But it gives you an idea of what the solutions roughly look like. It won't tell you what the solution is, but you can get an idea. Right? So here's a couple. Right? Now the first thing to note is that differential equation dy dx equals y squared minus x squared is called a Riccati differential equation. Awful things, right? That one can be solved, but a lot of Riccatis can't, right? So, but that one can, but it is actually a lot of work. Solving Riccati differential equations is very, very, very complicated, and it's not guaranteed to work. Right? So sometimes it works, sometimes it doesn't. There's another type of first order differential equation called an Abel differential. So a Riccati differential equation is basically where there's a y squared. Right? So it's non-linear. Abel is one where you get a y squared plus y. And for some inexplicable reason in applied maths, in lots of areas of maths for example, you will get this, you're modelling something in the real world. So I do fluid mechanics. So you're modelling this fluid mechanics problem, you make some assumptions and, you get this differential equation. And I swear to God, every fucking time you get an Abel differential equation. Right? And every time you scream, kick something, find out if it's one that can't be solved, you're screwed. Right? I think any applied mathematician that comes up with a general solution of an Abel differential equation will be very famous. We've all tried and we've all failed. Right, myself included. Right? But we can at least get a feel for the solution. Right? I mean, because if I can't solve it, what am I going to do? Well, I could solve it approximately. I could make some assumptions. You know, and so there's lots of approximate solution or numerical techniques. But if you want to make sure has it worked, you know roughly what they look like. Right? That's what the direction field tells you. Okay? Right, so basically this is how the direction gives us lots of little arrows, and you can trace a curve. As long as it follows the arrows, that will be approximately a solution. Okay? Right, so here's another one, as I said there, that one's here's one we can solve though. We're going to work out, this one is a first order linear differential equation. There is a standard solution technique that we can solve this one. We'll find out how next week. Right, but here I've got one where, well, all I know is the slope at every point x and y is 3y plus e to the x. So I could draw not by hand obviously, draw a slope field, and I could draw some solutions. So there's one that goes through the point x equals 0, y equals minus 1, so that's got to be the one down below. You notice how they just sort of follow the arrows. Yeah? Again, obviously we can't do this by hand, but there is, I've talked about this website for plotting, this Wolfram Alpha website. You can actually use this to create slope fields in a roundabout kind of way. Let me show you how. So if you click on this link, which I've done here, and if you search for direction field, right, it'll come up with an example that you can play with. Hurry up. Right? Now, notice it's got a thing called a vector field. Don't worry about what that means for the moment. But if you, right, a vector field is for us is a picture of lots of little vectors on it. Right? So this is a vector field. It is a particular vector field. Now, if you type in, to make the vectors all have length 1, we want them to be unit vectors. Right, so if you enter the vector field as, remember, basically a vector, I said here, it's a little thing, where is it? Where this, but I want this to be a unit vector. Right, so the length of this vector is the square root of 1 plus dy dx all squared. Yeah? So if you enter it like that, right, so that's just, I'm making it a unit vector. Right, so what have we got here? This one was f equals 3y, dy dx equals 3y plus e to the x. So if I make this 1 over the square root of 1 plus 3 times y plus the exponential of x all squared, square rooted, and then what bit do I want? Oh, then I copy this and put this there. So that's, I need this to be dy f or dy dx divided by this. Fingers crossed. Oh, hang on, this is going x minus 10 to 10, y is minus. So what did I do here? Minus, right? So if I play around with the x, lower limit of x is minus 2 to 2, y goes from minus 2 to 2. Work. You're going to make me a liar. Right, that looks about. You see? Right? So you can use this to generate them. Obviously, the way I generate in the lecture notes is a lot better, right? But I think you've got to pay to get this to do really nice plots, and hell with that. Right? But you can generate these yourself. You certainly wouldn't do this by hand, right? So the type of questions I would give you for these is I would give you a direction field and ask you something about it. Like I would never, don't think you need to bring a little ruler and frickin' protractor and I'm going to get you to draw one. That ain't going to happen, right? Let me show you the type of questions I give you. Right? So in the practical class next week, there will be this question. Right, this is the kind of thing I'll ask. For the direction field shown in each plot or graph below, decide whether it matches a differential equation for which the slope depends on x only, on y only, or on both x and y. So in other words, do these correspond to dy dx equals a function of x only, dy dx equals a function of y only, or dy dx is a function of both x and y? Now think about that carefully. If it involves x only, that should mean no matter what the value of y, the slope is unchanged. Yes? Right, so any horizontal line, any particular y, all the slopes will be the same. Right, now you look at this one, well that's not happening. This one it is though. Look, for a particular value of y, all the slopes stay the same, don't they? Right? So this one can't, the right-hand side can't depend on y. This one it must. Now if it was not involving x, that means vertical lines wouldn't change. Well here you can see a vertical line here, the slopes change. Right? So that means as I move along x, two different values of x have two different slopes. It's got to depend on x. So this one's a function of x only, but this one's got to be a function of both x and y. Right? That's the sort of thing I'll ask. I mean, I'm going to upload the final exam from last semester next week anyway to talk about in the last lecture, but there's also, just make sure I am opening the right one. I have done that before. All right? We're going to talk about it. You're getting this next week anyway, but here's a question from the exam from last semester, one of the multiple choice questions. All right, so here I said, consider the following slope field. Which of the following differential equations is this slope field for? 1 plus x, x squared, x plus y, x on y, or log of y. Well, if you look at it, you can see, well, for particular values of, so horizontal lines, the slope changes, doesn't it? Right? But for vertical lines, it doesn't. So that means that the slope field's got to be, it varies with y, but not x. Right? So, oh, hang on, have I done that the wrong way around? Sorry. So for constant x, so as x changes, the slopes changes, but as, what am I trying to say here? If you look at vertical lines, as y varies, so vertical lines, as y varies, the slope doesn't. Yeah? So it's got to be a function of x only. Right, so that immediately eliminates C, D and E, doesn't it? So now you've got to decide, is it A or B? Well, what is that saying? Well, B is saying, well, that when along the line x equals 0, the slopes would be 0. So along the line x equals 0, the slopes are definitely not 0, are they? But this one is saying that, well, when x equals minus 1, the slope should be 0. Right? And the slopes are horizontal there, so it's got to be A. Right? So that's the sort of thing I will ask. If I'm going to I'm not going to get you to draw one. I'm going to get you to, I'll give you one and do something with it. But if you do want to draw your own, just follow the instructions on this last slide, right? And you can use this Wolfram Alpha to draw some. Next week, in the 2 lectures next week, we'll start actually solving some of these, okay? But we'll leave it there for today. All right, so yeah, I'll see everyone next week.